The branch of physics which deal with study of electric force, electric fields, electric potential and electric energy due to electric charges at rest is known as electrostatic. There are many examples. For example, a mild shock is felt when metallic door of the car is touched after sliding over the seat of the car. Spark is seen, crackling sound is heard when synthetic shirt is taken off in the dark in the dry weather or lighting in the sky, etc. The electricity developed on the object when they are rubbed together is known as friction electricity. Because the charges do not move, it is also termed as static electricity. The physical quantity which is related to excess or deficiency of electron is known as electric charges. It gives rise to electric force between proton and electrons. It is a scalar quantity. There are two types of charges, positive and negative. The process by which substance acquire electric charges is known as electrification. The charge on one proton is 1.6 10 raised to minus 19 coulomb and electron is minus 1.6 into 10 raised to minus 19 coulomb. When two objects are rubbed together, electron from the outermost orbit of one object get transferred into another object by acquiring thermal energy. The object which lose electron get positive charge and the object which gain electron get same amount of negative charge. The substances which allow electricity to pass through them are called conductors and which do not allow the electricity to pass through them are called insulators. Electric charge has additive nature, that is the total charge of any object is algebraic sum of individual charges on different parts of the object. Total charge of an isolated system always remain conserved. Total charge on any object is the integral multiple of basic elementary charge. This is called quantization of charge. Q is equal to plus minus Ne. Then there is comparison between electric charge and mass. There are some numericals based on the quantization of charge. Coulomb law states that force of attraction or repulsion between two charges Q1 and Q2 placed in vacuum at rest is directly proportional to product of the magnitude of the charges and inversely proportional to the square of the distance r between them. F is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon r square, where epsilon naught is absolute permittivity of free space. 1 upon 4 pi epsilon naught is equal to 9 into 10 raised to power 9 Newton meter square per coulomb square. 1 coulomb is that charge which repels same charge with a force of 9 into 10 raised to power 9 Newton when placed in vacuum at a distance of 1 meter from it. Permittivity is the property of the medium by virtue of which it affects the electric force between the charges. It is defined as the ratio of electric force between the two charges placed at certain distance apart in vacuum to force between same charges placed at same distance apart in medium. By writing Coulomb law in vector form, we find that it obeys Newton's third law of motion. We can write force between two charges in terms of their position vectors. Force on charge Q1 at location R1 due to charge Q2 at location R2 F12 is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R12 modulus Q into R12 vector. According to principle of superposition, total force on a given charge due to number of charges around it is equal to vector sum of individual forces acting on it due to all other charges. Limitations of Coulomb law are that it is applicable to fixed point charges at rest, it is medium dependent law, it is experimental law, it is applicable to few kilometer distance, it loses its validity for a distance less than 10 raised to power minus 15 meter. The space around a charge within which its effect can be felt by any other charge is called electric field. The point charge whose electric field is to be studied is called source charge. Infinitely small charge used to experience electric force is called test charge. Electric field intensity due to a source charge at a point is defined as the force experienced per unit positive test charge placed at that point. The concept of electric field is used to find the force on a charge placed in the electric field of some another charge. Electric field intensity when source charge is at origin. E is equal to 1 upon 4 pi epsilon naught Q upon R naught modulus cube into R naught vector. When source charge is away from origin, then electric field is equal to 1 upon 4 pi epsilon naught Q upon R naught minus R vector modulus cube into R naught minus R vector, where R naught is the position vector of point of observation and R is the position vector of point charge. Electric field at any point due to number of charges is vector sum of electric field due to individual charges at that point. Electric field line is a path along which a unit positive charge will move if it is free to do so. It starts from positive charge and end at negative charge. It may be curved or straight path. Tangent at any point gives the direction of electric field intensity at that point. No two field line cross each other. If they cross, then at point of intersection there will be two directions of electric field, which is not possible. They do not pass inside the conductor. A pair of equal and opposite charges separated by a fixed distance is called electric dipole. Product of magnitude of either charge and the length of the dipole is called dipole moment. It is a vector quantity having direction from negative to positive charge and units are coulomb meter. Molecule is said to be polar molecule if center of mass of positive charge do not coincide with center of mass of negative charge. If coincide, then it is called non-polar molecule. Polar molecule have permanent dipole moment, whereas dipole moment is induced in non-polar molecule also when they are placed in external electric field. Electric field intensity on the axial line of an electric dipole is equal to 1 upon 4 pi epsilon naught 2 pr upon r square minus a square whole square. Its direction is from negative to positive charge. Electric field intensity on the equatorial line of an electric dipole is E is equal to 1 upon 4 pi epsilon naught minus p upon r square plus a square raised to power 3 upon 2. Its direction is opposite to dipole moment, that is from positive to negative charge. When dipole is placed in external uniform electric field, it experiences a torque. Tau is equal to P cross E vector. Maximum torque is experienced when electric field is perpendicular to dipole moment. Energy is stored in electric dipole when placed in uniform electric field. U is equal to minus P dot E. A system of closely spaced electric charges make a continuous charge distribution. Charge per unit length is called linear charge density. Charge per unit surface area is called surface charge density. Charge per unit volume is called volume charge density. Now there are some numericals. A vector normal to the area having magnitude equal to the area of the surface and direction perpendicular to the surface is called area vector. Total number of electric lines of force passing through a surface held in the path of electric field is called electric flux. It is equal to E dot ds. It is a scalar quantity. Gauss law states that total electric flux through any closed surface in vacuum is equal to 1 upon 4 pi epsilon naught the total charge enclosed by the surface. Any imaginary closed surface around a charge used to find electric field at that point is called Gaussian surface. Gauss law is used to find the electric field intensity due to continuous charge distribution. We can derive Coulomb law from the Gauss law. We can find electric field intensity due to long infinitely straight line charge using Gauss law. It comes out to be E is equal to 1 upon 2 pi epsilon naught lambda upon r, where lambda is the linear charge density and r is the distance of point of observation. We can also find electric field intensity due to uniformly charged infinite plane sheet. It comes out to be E is equal to sigma upon 2 epsilon naught, where sigma is the surface charge density. Therefore, electric field intensity due to two infinitely plane parallel sheets of charge having equal and opposite charge comes out to be E is equal to sigma upon epsilon naught. Similarly, we can find electric field intensity due to uniformly charged spherical shell. It comes out to E is equal to 1 upon 4 pi epsilon naught q upon r square. And no electric field exists inside spherical shell. Now we have some examples, numericals.